Hello students, welcome back to GATE Electronics Guruji classes. So by now we have already completed the concept of limit, and in this video we will solve some problems based on the concept of limit. So let us come to the first problem. So the first problem that we need to solve is limit extending towards 0 e to the power x minus 1 plus x square by 2 divided by x cube. So let's solve the problem. See, we observe that we have a function here which is given in the form of a fraction. The numerator of the fraction is e to the power x minus 1 plus x square by 2, and the denominator of the fraction is x cube, and we have to find out the limiting value towards which this function tends to when the limiting variable x tends towards 0. Now observe. You see that when x is tending towards 0, let me use another color. You see that when x is tending towards 0, e to the power x minus 1 plus x square by 2 tends towards, so e to the power x minus 1 plus x square by 2 tends towards, see, when x is tending towards 0, e to the power x will tend towards e to the power 0 minus 1 plus, when x is tending towards 0, clearly this x is also tending towards 0, and when x is tending towards 0, x square by 2 will tend towards 0 square by 2. So if I simplify this, I will have 1, e to the power 0 is 1 minus 1 equal to 0. So I observe that when the limiting variable x is tending towards 0, e to the power x minus 1 plus x square by 2 tends towards 0. And what is the denominator? X cube. And you see that when x is tending towards 0, x cube will tend towards 0 cube, which is nothing but 0. So what you observe is when the limiting variable x is tending towards 0, the numerator of the fraction as well as the denominator of the fraction both are tending towards 0. We see that e to the power x minus x square by 2 is tending towards 0, as well as x cube is also tending towards 0. So clearly this function is taking a 0 by 0 form, right? So we observe that when the limiting variable x is tending towards 0, this function is present in a 0 by 0 form. And we know that whenever we have a 0 by 0 indeterminate form, we use the L'Hospital rule. And what do we do in L'Hospital rule? We differentiate the numerator and denominator separately with respect to x, and again we apply the limit. So in this case, if I differentiate the numerator, that is e to the power x minus 1 plus x square by 2 with respect to x, if I differentiate the numerator with respect to x, I will have e to the power x minus 0 plus 1 plus twice of x divided by 2. If we differentiate e to the power x with respect to x, I will have e to the power x. If I differentiate 1 with respect to x, we will have 0. If we differentiate x with respect to x, we will have 1. If we differentiate x square by 2 with respect to x, I will have twice x by 2, because differentiation of x square is nothing but twice x. And if I now differentiate the denominator, that is x cube with respect to x, I will have 3 times of x square, right? Because differentiation of x cube with respect to x is 3 times of x square. Now if I simplify this, I will have limit of x tending towards 0 e to the power x minus 1 plus x divided by 3 times of x square, right? I can take these 3 outside. So if I take this 3 outside, a 1 by 3 will come out, right? Now see, again observe. Now what do we have? We have a function e to the power x minus 1 plus x divided by x square, and we have to find out the limiting value, the limiting value of this function when the limiting variable x is tending towards 0, right? Now see, you observe that when x is tending towards 0, e to the power x minus 1 plus x will tend to You see, when x is tending to 0, e to the power x minus 1 plus x will tend towards e to the power 0 minus 1 plus 0, which is nothing but 0, and the denominator, that is x square, will tend towards 0 square, which is 0. So what you observe is, when x is tending towards 0, both the numerator and the denominator are tending towards 0. So clearly this function is present in a 0 over 0 form. This function is present in a 0 by 0 indeterminate form. So we will again have to use L'Hospital rule on this function. So we have to differentiate the numerator and denominator separately with respect to x. So if I differentiate the numerator with respect to x, I will have e to the power x minus 0 plus 1, because differentiation of e to the power x with respect to x is e to the power x, differentiation of 1 with respect to x is 0, and differentiation of x with respect to x 1 divided by differentiation of x square with respect to x is nothing but twice x, right? Now I can take this 2 outside. So if I take this 2 outside, this will get multiplied with 1 by 3 and I will have 1 by 6 outside into limit of extending towards 0 e to the power x minus 1 divided by x. Now see, now observe one thing. This limit is already a standard limit which value should already be known to you, right? Limit extending towards 0 e to the power x minus 1 divided by x is a standard limit whose value should already be known to you. And we know that the value of this standard limit is 1. So I will have finally the answer 1 by 6 multiplied by 1 equals to 1 divided by 6, right? So the final value of this answer is 1 by 6. Keep in mind one thing, that this particular limit extending towards 0 e to the power x minus 1 by x can also be solved using the L'Hospital rule, because this is also present in a 0 by 0 form. But as we already know the value of this limit as a standard limit, so there is no need to use L'Hospital rule again. We can directly write the value from the standard limit. So the final answer of this problem is going to be 1 by 6. Okay. So now let us come to the second problem. So the second problem is limit extending towards 0 sin square x by x. This problem came in mechanical engineering branch in 2007, I think, as much as I can remember. So let's solve the problem. It's an easy problem. See, here we have a function sin square x divided by x, and we have to find out the limiting value of this function when the limiting variable x is tending towards 0, right? Now see, when x is tending towards 0, then sin square x will tend towards sin square 0, right? When x is tending towards 0, then sin square x will tend towards sin square 0. Sin square 0 is nothing but 0, and x is tending towards 0, right? So we observe that the numerator, that is sin square x, is tending to 0, and the denominator, that is x, is tending to 0. So clearly sin square x by x is present in a 0 by 0 indeterminate form, right? So if this function is present in a 0 by 0 indeterminate form, then we have to use L'Hospital rule. So what do we do in L'Hospital rule? In L'Hospital rule, we differentiate the numerator and denominator separately with respect to x. Here the numerator is sin square x. If we differentiate sin square x with respect to x, we will have twice of sin x into cos x. And if we differentiate the denominator with respect to x, we will have 1, because differentiation of x with respect to x is 1. So we have twice of sin x into cos x, and we know that 2 times of sin x into cos x is nothing but sin of 2x, right? And see, when x is tending towards 0, then sin of twice x will clearly tend towards sin of 2 into 0. Sin of 2 into 0 is nothing but sin of 0, that is 0. So the limiting value of this function is nothing but equal to 0, right? So 0 is the final answer. Alright? Okay. So this is an easy problem. So now let's move to the third problem. So the third problem says that we have a function fx such that fx is equal to x when x is varying from 0 to 1, and fx is equal to 3 minus x when x is greater than or equal to 1 and lesser than or equal to 2. And we have to check the existence of limit at x equal to 1. So observe the function. You see that when the value of x is varying from 0 to 1, then fx is x, and when x is varying in the interval 1 to 2, then fx is 3 minus x. So clearly the value of the function fx or the expression of the function fx varies from one interval to another interval. When the value of x is varying in the interval 0 to 1, then fx is having one expression, that is x. When the value of x is varying in another interval, that is 1 to 2, then the expression of fx comes as 3 minus x. This kind of functions are called as piecewise defined functions because the expression of this kind of functions varies from one interval to another interval. Clear up to this part? Okay. Now we have been asked to check the existence of limit at x equal to 1, and we already know how to check the existence of limit. We have to first check the existence of left hand limit, then we have to check the existence of right hand limit, and then we have to check whether the left hand limit is same as the right hand limit or not, right? So we will first calculate, that is, we will first check the existence of left hand limit here, right? Now observe one thing. Suppose this point on the number line, not number line, suppose this point corresponds to x equal to 0, and suppose this point is x equal to 1. Let me make this one as 1. Suppose this is x equal to 2, and suppose this is x is equal to 0, right? And we have been asked to check the existence of limit at this point, that is x is equal to 1, right? Now observe that when x is varying from 0 to 1, then fx is x. So when x is varying from 0 to 1, here fx is same as x. And when x is varying from 1 to 2, then fx is same as 3 minus x. Fx is 3 minus x, right? So just in the left hand side of x equal to 1, the expression of fx is x, and just in the right hand side of x equal to 1, expression of fx is 3 minus x, right? So when we will check the left hand limit of the function fx at x equal to 1, then we are approaching towards x equal to 1 from the left hand side, right? So then we will take fx at x, right? And when we check the right hand limit of the function fx at x equal to 1, then we approach towards x equal to 1 from the right hand side, right? And then we will take fx as 3 minus x. I hope it's clear. So first find out the left hand limit. So the left hand limit of the function fx at x equal to 1, which is denoted by limit of fx as x tends towards 1 minus, will be same as limit of extending towards 1 minus, fx will be replaced by x as I explained, and limit of x when extending towards 1 minus is nothing but 1, right? Now let us calculate the right hand limit. The right hand limit of the function fx at x equal to 1, which is denoted by limit of fx when extending towards 1 plus, will be equal to limit of 3 minus x when x is tending towards 1 plus. Why? Because we know that when we find out the right hand limit, when we estimate the right hand limit, when we evaluate the right hand limit, then we approach towards x equal to 1 from the right hand side. And just in the right hand side of x equal to 1, the expression of fx is 3 minus x, and that's why fx has been replaced by 3 minus x. And limit of 3 minus x when extending towards 1 plus is nothing but 3 minus 1, that is 2, right? So the left hand limit of the function fx at x equal to 1 is 1, whereas the right hand limit of the function fx at x equal to 1 is 2, right? So the left hand limit is not same as the right hand limit. So what do we have? We have the left hand limit of the function fx at x equal to 1 is not same as the right hand limit of the function fx at x equal to 1, right? So clearly the limiting value does not exist. So the limiting value of the function fx at x equal to 1 does not exist, right? Because for the limiting value to exist, the left hand limit has to be same as the right hand limit. Here the left hand limit is not same as the right hand limit. So clearly the limiting value of the function fx at x equal to 1 does not exist, right? Now let us move to the next problem. This is the next problem that we are going to solve. It says that fx is equal to sine of greatest integer function of x divided by greatest integer function of x when greatest integer function of x is not equal to 0. Okay. And the value of fx is 0 when greatest integer function of x is equal to 0. And we have to find out the limiting value of the function fx when x is tending towards 0, right? So I hope that each and every one of you knows what do we mean by greatest integer function. Suppose we have a number 2.5 and suppose we have to find out the greatest integer function of the number 2.5. How do we find out this? You have to find out what is the integer. You have to find out what is the integer which is just smaller than or equal to 2.5. Now 2.5 खुद तो एक integer नहीं है ना. So we have to find out the integer which is just smaller than 2.5. What is the integer which is just smaller than 2.5? Nothing but 2. So greatest integer function of 2.5 is 2. Now suppose we want to find out greatest integer function of 3. 3 is itself an integer, right? And I said that you have to check what is the integer which is just smaller than or equal to 3. 3 is itself an integer. So greatest integer function of 3 will be equal to 3. Okay. Suppose you want to find out greatest integer function of minus 1.7. Is minus 1.7 an integer? No, it's not an integer itself. So you have to find out the integer which is just smaller than minus 1.7. What is the integer which is just smaller than minus 1.7? Nothing but minus 2. So greatest integer function of minus 1.7 is minus 2. What is the greatest integer function of minus 4? Is minus 4 an integer? Yes, it's an integer itself. So greatest integer function of minus 4 is minus 4 itself, right? So I hope that this idea is clear. This should already be known to you from class 12, okay? So now let's look at the problem. The problem says that fx is 0 when greatest integer function of x is equal to 0. And when greatest integer function of x is not equal to 0, then fx is equal to sine of greatest integer function of x divided by greatest integer function of x, right? Now, when greatest integer function of x is 0, clearly when x varies in the interval, greater than or equal to 0 but strictly lesser than 1, in this interval the greatest integer function of x is 0, right? Take any number in this interval, say 0.5. What is the greatest integer function of 0.5? Nothing but 0, because the integer just smaller than 0.5 is nothing but 0, right? Now if you take say 0.8, what is the greatest integer function of 0.8? Nothing but 0. Because the integer which is just smaller than 0.8 is 0. What is the greatest integer function of 0? 0 is an integer itself. So the greatest integer function of 0 will be 0 itself. So clearly you observe that when x is varying in the interval greater than or equal to 0 but strictly lesser than 1, in this interval greatest integer function of x is equal to 0. So outside this interval, anywhere greatest integer function of x is not equal to 0, right? We observe that in this interval greatest integer function of x is 0. So clearly outside this interval greatest integer function of x is not equal to 0. So what is the outside of this interval? Nothing but when x is lesser than 0 or when x is greater than or equal to 1, right? So in this interval greatest integer function of x is not equal to 0. If anyone wants to know how did I get this, I said that greatest integer function of x is 0 when x is varying in the interval greater than equal to 0 and lesser than 1. So outside this interval greatest integer function of x is not equal to 0. Now what is the interval which is outside this interval? See here, x was greater than or equal to 0 but strictly lesser than 1. So outside this interval means when x is strictly lesser than 0 but x is greater than or equal to 1, right? So in this interval, greatest integer function of x is not equal to 0. Okay. Now see. Suppose this point corresponds to x is equal to 0 and suppose this corresponds to x is equal to 1, right? You see that when x is varying in the interval greater than or equal to 0 but lesser than 1, in this interval fx is 0. So in this interval fx is 0. When x is lesser than 0, then fx is equal to sine of greatest integer function of x divided by greatest integer function of x, right? Or when x is greater than or equal to 1, then also fx is sine of greatest integer function of x divided by greatest integer function of x. So when x is greater than 1, that is in the right side of x equal to 1, I will have fx equal to sine of greatest integer function of x. I will have fx as sine of greatest integer function of x divided by greatest integer function of x. And we have to check the limiting value of the function at x equal to 0, right? And how do we do it? We know that we first find out the left hand limit, we then check the existence of right hand limit, and then we check whether the left hand limit is same as right hand limit or not, right? So we know that when we calculate the left hand limit at x equal to 0, we tend towards x equal to 0 from the left hand side. So clearly, while finding the left hand limit, I will take fx as sine of greatest integer function of x by greatest integer function of x, because when x is lesser than 0, then the expression of fx is this, right? When we evaluate the right hand limit at x equal to 0, we tend towards x equal to 0 from the right hand side, right? So, and we observe that just in the right side of x equal to 0, the value of fx is 0, right? Just in the right side of x equal to 0, the value of fx is 0. So clearly while evaluating the right hand limit of the function fx at x equal to 0, I will take fx equal to 0 because just in the right side of x equal to 0, fx has a value of equal to 0. So clearly you observe that the right hand limit of the function fx at x equal to 0 is nothing but 0, because just in the right side of x equal to 0, we have fx equal to 0. Now find out the left hand limit. Left hand limit is denoted by limit of fx when extending towards 0 minus, which will be same as limit of extending towards 0 minus sine of greatest integer function of x divided by greatest integer function of x, right? Why? Because see, just in the left hand side of x equal to 0, the expression of fx is sine of greatest integer function of x by greatest integer function of x, and that's why we have replaced fx by sine of greatest integer function of x by greatest integer function of x, right? Now observe very carefully. See, when you are moving towards x equal to 0 from the left hand side, that is when we are evaluating the left hand limit at x equal to 0, we are not interested about the value of the function at x equal to 0, right? While evaluating the left hand limit at x equal to 0, we are not interested to calculate the value of the function at x equal to 0. That's not what left hand limit means. Left hand limit means that when we are moving closer and closer and closer towards x equal to 0, I have to check towards which value the function fx tends to, right? Now observe that in the left hand side of x equal to 0, suppose this is x equal to minus 1, okay? Let me use the black color. Suppose this is x equal to minus 1. So just in the left hand side of x equal to 0, that is in the left neighborhood of x equal to 0, if I take any point, this will have a value between minus 1 and 0, right? I hope it is clear. If I take a point just in the left hand side of x equal to 0, that point will have x coordinate between minus 1 and 0. And I know that the greatest integer function of any value of x such that x is lying in the interval minus 1 to 0 is nothing but minus 1. we know that when x is varying in the interval -1 to 0, the greatest integer function of x is strictly equal to -1, right? So just in the left hand side of x equal to 0, if I take a point, this will have greatest integer function value as -1, right? See, we are not interested to check the value at x equal to 0. In left hand limit, we are interested about the behavior of the function just in the left hand side or in the left neighborhood of x equal to 0. So if I take any point just in the left hand side of x equal to 0, this will clearly lie in this interval, that is -1 to 0, right? And in this interval, the value of greatest integer function of x is -1. So clearly this limit will have a value of sine of -1 divided by -1. If we simplify this, this will come as equal to sine 1. Is it clear? I am again repeating, when we are evaluating the left hand limit at x equal to 0, we are not interested about the value of the function at x equal to 0. Rather, we want to check the behavior of the function in the left neighborhood of x equal to 0. And you observe that just in the left hand side of x equal to 0, that is in the left neighborhood of x equal to 0, just in the left hand side of x equal to 0, if you take a value of x, then clearly x will lie in this interval, that is -1 to 0. This is -1, this is 0. If I take any point just in the left hand side, I am saying just in the left hand side of x equal to 0, then clearly x will lie in the interval -1 to 0. And in this interval, the greatest integer function has a value of -1. So here the right hand limit is 0, whereas the left hand limit is sine of 1. See, the right hand limit of fx at x equal to 0 is 0, whereas the left hand limit of fx at x equal to 0 is nothing but sine 1. 0 is clearly not equal to sine 1. So the right hand limit is not same as the left hand limit. So clearly the limiting value of this function fx at x equal to 0 does not exist. DNE means does not exist. So I hope that the concept is clear. So I think that I had already solved 4 to 5 problems while explaining the theory. I also solved 4 problems here. That's enough for limit. And if you face any difficulty to solve any problem, then please let me know in the comment section. You can also email me this problem in email ID guruji@gmail.com, right? If you have any difficulty to solve any kind of problem, if you need a good problem set, then let me know in this email ID getelectronicsguruji@gmail.com. Okay, so if you still haven't subscribed to the channel, then please do subscribe to the channel, because see, we put this amount of efforts for you people, right? So obviously we also hope that some kind of appreciation will come from your side. And so it's our request that please subscribe to the channel, like this video, share these videos with your friends. So I will meet you in the next video. Thank you.